Hello everyone, in this video I will be presenting faster multi-sided one-band boundary labeling. I am Devajyoti Mandal from University of Saskatchewan, and this is a joint work with Prosenjit Bose and Syed Mehrabi from Carleton University. We can often see different types of labeling in the diagrams. For example, you can see here a plant and different labels for leaves, flowers, and others, and here is another diagram where you have labels on both sides of the diagram. Here is another schematic diagram where you have labels on the top, left, bottom, and also on the right. Boundary labeling problem actually models all this diagram labeling in a simple setting. So you have ports along the boundaries and you have the same number of sides inside the rectangle. And our goal is to figure out an assignment of the ports to the sides. As we can see here, we have one leader for each pair of port and side, and the leaders are disjoint. No one is crossing another one. So we need a set of disjoint leaders between sides and ports. And we say this is a decision problem. Sometimes a solution may not exist. This is a simple input and you have only two sides, and the top port and the right port can be connected to these two sides in only a few ways, and however you connect them you will have a crossing, and that's why this is an input for which the answer is negative. So we can talk about k-sided boundary labeling, so where k is 1 to 4. So let's take a look at the known literature with these different values of k. So here in the first case, k is 1. You have only the ports lying along the right side of the rectangle, and then you have ports on opposite sides, and then you have ports on adjacent sides. Here you have k equals 3, and finally you have k equal 4. Now in 2004, Bose et al. Showed that in the first and the second case, you can always find a feasible assignment in order n log n time. However, in that time, the adjacent case were not looked at. But for the case where k is larger than 2, they show that if you allow 2 bands per leader, then you can always find order n log n time solution. Later on, Kindermann et al. Examined this case where you have ports on two sides. In this case, you can find a solution if it exists in order n square time. They also show that if the ports lie on all three sides of the rectangle, then there is a solution that takes order n to the power 4 time. And if there are ports on all sides of the rectangles, then it takes order n to the power 9 time. Later on, this has been improved to order n to the power 6, and in this paper we want to improve this further. For k equal 3, that is three-sided case, we improve it from n to the power 4 to n to the power 3 log n, and for the four-sided case we improve it to n to the power 5. Now first let's take a look at the three-sided case. Now in the three-sided case, we want to devise an n cube log n time algorithm, but let's first take a look at the known approach. Kindermann et al. First considered the grid defined by taking vertical and horizontal lines through each port and each side, and that gives us this type of grid. Kindermann et al. Showed that if there exists a crossing free solution, then there is one where you can partition it using a two-band polygonal chain like this. Now you can see an example here. This is a positive solution, and we can see there is a partition like the one that goes through the grid point. Okay, so now we have order n square grid points, and for each grid point there are order n ways to define this partition. That means we have order n cube subproblems. Now Each of these subproblems are actually two-sided subproblems, and Kindermann et al. Showed that two-sided problems can be solved in n squared time, and that means we have a solution of n cubed times order n square. In fact, they showed that this running time can be improved to order n to the power 4 time. And here we want to improve it further by using the following approach. For each grid point, we first project it on the top of the rectangle boundary, and then we figure out a balanced partition with one bend polygonal chain. So by balanced, we want to make sure that the left part has equal number of sides and ports, and the right side also have equal number of sides and ports. And we know that there is a partition like this for a grid point if there exists a separating solution. And when you partition it like this, then the partition can actually take different shapes. So in this case, you can see this is kind of a gamma shape, and this is similar to an L shape. Now, based on this idea, we partition these subproblems into L type and gamma type like this. Now, when you see this is an L-shaped problem, the opposite part is a gamma-shaped, but this is a reverse gamma shape. So when we call that a problem is of L-shaped type, then that means it is L or a mirror reflection of L. Similarly, for gamma shape, we consider gamma or mirror reflection of gamma. To solve this L-shaped or gamma-shaped problem, we use a dynamic programming that further decomposes these shapes into smaller subproblems. We only consider the L-shaped problem here, and the gamma-shaped problem is a bit more involved, so we do not discuss it in this presentation. Now consider this L-shaped subproblem. Since the subproblems are balanced, I know that there must be a side on this vertical line. Let Q be that particular side, and there can be two cases. Q can be connected to one port on the left or one port at the top. If I know that there are ports on the left side, then I can always choose the bottommost port, and that gives me a L shape. And if there is no port on the left side, then I can queue to the first port at the top level, and that will also give me an L shape. And how do I express this L shape? Since we are using a dynamic programming, we use that the subproblem definition is something like x, li, left. That means this is the grid point and this is the li. By left, we mean that Q is connected to a left port. And similarly, we have here x and tk, and by top we denote that Q is connected to a top port. Now note that we do not have Q explicitly here, but once we are given this problem, based on the definition of the balanced problem, we can find this point Q. Now this is how we decompose an L shape. So here we got an L shape which is x, li, and this is the left case. And we find the point Q and then sweep the line, vertical line through Q to the left until I hit the point P. Now if P is to the right of X, then I seek for ports on the left side of the subproblem, and if there are some ports, then I pick the bottommost one and connect it to P, and I know that this is a safe option, and that means I get another smaller L type subproblem, and we are done for this particular case. If I see that there are no ports on the left side, then I know that this is a balanced subproblem, so I must have ports on the top, and I pick the first port on the top, this is that case, and then I again get a smaller subproblem which is of L shape. This can be done when P is to the right side of the vertical line through X. But what happens if P is to the left of the vertical line through x. In that particular case, for example, here you can see p is to the left of this red dotted line, and in this case we show that you can cut out a rectangular region, and this rectangular region is balanced. This balanced subproblem is a one-sided subproblem because you have ports only on one side. And what remains is a two-sided problem, and we know that two-sided problem can be solved in order n squared time, or can be checked whether there is a solution or not. This gives us a smaller size problem, and we pre-compute all such two-sided subproblems, and that's why we can do a table lookup. Now this is how we decompose an L-shaped left type subproblem. The top type subproblem is also similar, but for gamma shaped subproblem we need some more clever decomposition. Now eventually the summary is as follows. We have n square grid points, and still we have order n cube L and gamma shaped subproblems. And to solve these subproblems, we use an order n cube size dynamic programming table to store the solutions to this subproblem. But note that this dynamic programming actually decomposes this L and gamma shaped problem into further smaller subproblems, and we show that this decomposition can be found in log n time, and the number of problems we decompose it into is a constant number of subproblems. So that means to fill out all the entries of this table, we need order n cube log n time. We still need some preprocessing for the two-sided subproblems, as we have seen in the previous case analysis, but altogether that also take n cube log n time, and we get an algorithm with running time n cube log n. Now let's take a look at the four-sided case. And in this case, Kindermann et al. Showed that if there exists a crossing-free solution, then there is one that is partitioned. You can find a xy monotone orthogonal polyline that goes from one corner of the rectangle to the other corner, and you can also find another one that is minus x minus y monotone polygonal chain that connects the other two corners of the rectangle, and you do not have any crossing with these partitioning lines and the leaders. We will use this idea, but in a slightly different way, to get an algorithm with order n to the power 5 running time. If you have a partitioning orthogonal polyline like this red dotted line, then we can also find a set of maximal empty rectangles. So our dynamic programming take advantage of this sequence of maximal empty rectangles. Here is an overview of the process where we choose all possible ways to pick the first maximal empty rectangle, and then this empty rectangle must be bounded by two leaders, and the subproblems are expressed by these two leaders. Then we continue searching for the next maximal empty rectangle, and this is the next one in the sequence, and now you can see that the subsequent leaders actually partition this problem into three subproblems. We show that you can only have a constant number of subproblem types, and those subproblem types can be decomposed into further subproblems using dynamic programming that are also of the same types. And after bounding all these number of subproblems and filling out the dynamic programming table, we get a running time of order n to the power 5. This ends the discussion of the results in this paper, but we have some directions for future research. For example, can we figure out a faster solution to the problems that we discussed? In the previous literature, Kindermann et al. And Bose et al. Both considered the situation where the sum of the leader lengths are minimum, and in our case we only care about planarity. Now, can we actually minimize the total leader length within the same running time? And also we do not know any non-trivial lower bound on the time complexity. And that's all. Thank you for listening.